By this point, you can assign whether something is being oxidized or whether it's being reduced in terms of loss or gain of electrons. You can identify a reducing agent and an oxidation agent as well. What we're going to do now is we're going to have a closer look at the oxidation states. And the oxidation states are used to see what is actually being oxidized and what is being reduced in a redox reaction. Sometimes these oxidation states are called oxidation numbers or charges. So when we write down oxidation state or oxidation number or charge, more or less mean the same thing. However, charges you would only really use for an ionic compound. Oxidation state and oxidation number, again they are the same thing. You would use those terms when describing the charge in an ionic compound, but also the charge as if it were a covalent compound. So the idea of oxidation states is that each element in a compound is given an oxidation state. In an ionic compound, the oxidation state simply tells us how many electrons has been lost or gained compared with the element in its combined state. In a molecule, the oxidation state tells us about the distribution of electrons in a compound based on electronegativity. So the more electronegative an element is, the more negative the oxidation number. So we need to know some rules to assign oxidation numbers. So we'll start off with some very straightforward ones. Let's look at group 1. So if you've got a compound in group 1, for example NaCl, the sodium would always be +1. So no matter what compound I pick in group 1, that group 1 element, the oxidation state, is always +1. We know that because we need to remove one electron to get a full shell. The same rule applies for group 2 and group 3 as well. So an example of a group 2 element would be something like calcium chloride. So the charge or the oxidation state or the oxidation number of calcium here would be +2. Similarly, magnesium bromide again would be +2. Aluminium chloride or aluminium bromide, the metal there is +3. So group 3 are +3 charges. Fluorine is always -1. So fluorine is always -1. Now that does not apply to all other group 7 elements. So not always group 7 elements are -1. They're not always -1. In all of these ones, the group 7 elements are in fact -1. But there are quite a lot of compounds where the group 7 element is not -1. But fluorine in group 7 is always -1. And the reason why the fluorine is always -1 become clear later on, but the underlying reason is because fluorine is the most electronegative atom. Or I should say element there, because in this case it would be an ion. Okay, so let's have a look at some exceptions then. So hydrogen is usually +1. So you would have seen the H+ ion quite a bit. For example, the 3 most common acids, HCl, HNO3, H2SO4. The oxidation state is +1 in all of those. Sometimes though, however, hydrogen can be -1. So it can be -1. For example, if we look at this chemical formula here. Now, we need to consult 2 rules here. We need to consult the hydrogen rule because it's got hydrogen in it, but also the group 1 rule because it's got a group 1 element in there. Now we said that anything in group 1 always has an oxidation state of +1. Always. That's always the case. Therefore, that Na there must have an oxidation state of +1. Therefore, the hydrogen must have an oxidation state of -1 to balance the charge. I have a +1 there and a -1 there. A +1 and a -1 will balance the charge because overall it should have no charge. We call an H+ ion just a hydrogen ion. An H- ion, it's got a slightly different name, however. It's called a hydride ion. So a hydride ion has an oxidation state of -1. And you usually get that when hydrogen is bonded to a metal. For example, in this particular case, it's sodium. Okay, the next one is oxygen. Now, oxygen is in group 6 of the periodic table, isn't it? If it's in group 6 of the periodic table, it needs 2 more electrons for a full shell. If it needs 2 more electrons for a full shell, it would normally have an oxidation state of -2. And that is usually the case. However, there are some exceptions. So in peroxides, the oxidation state of oxygen is -1. So it's O-. Now you need to know what a peroxide actually is. So a peroxide ion is this. So that there is a peroxide ion. A peroxide ion is made up of 2 of these. So that is equal to that and that added together. We've got 2 oxygens, 1, 2, and a -1 charge and a -1 charge. That makes 2-. I'll give you an example of a peroxide. So the most simple example I can think of is hydrogen peroxide. So hydrogen peroxide is often used in hair dye. So the chemical formula of hydrogen peroxide is H2O2. The hydrogen there is +1. I've got 2 of them though. So I have 2 hydrogens that are both +1. So I write down +1 and +1. Therefore, on all of this, on all of the O2 there, it must be a 2- because the peroxide ion is O2-. O2, 2-. So each of these oxygens must have a -1 charge. So overall there, that's got no charge. Hence we have an O- here. So if you were asked, what is the oxidation state of oxygen in hydrogen peroxide, you would say -1. You would not say -2. You would say -1 because you're asked what is the oxidation state of the oxygen. You're not asked what is the oxidation state of 2 oxygens. Likewise here, if you were asked what is the oxidation state of hydrogen here, you would say +1. You wouldn't say +2. So the oxidation state of hydrogen here is +1. It's +1 there. It's also +1 there, guys. It's not +2. Just because you've got 2 of them, it doesn't mean you've doubled the oxidation state. You just have 2 ions in there with a +1 charge. Okay. Another example is this molecule here. Now this is an interesting molecule because what you've got here is you've got oxygen and fluorine. Remember, we've got a fluorine rule. Here's our fluorine rule. Our fluorine rule is fluorine is always -1. So each of these fluorines in here must be -1. So I'm going to write -1 down, -1 down again because there's 2 of them. So there's a 2- charge on all of the F2 here. Therefore, there must be a +2 charge on the oxygen. So in this particular case, oxygen has a charge of +2. Its oxidation state or oxidation number of oxygen there is +2. Okay, there are some rules. We've given an example of each rule. Now let's try and apply all of those rules to some questions. What we're going to do now is we're going to assign oxidation numbers to some compounds. So this one's called phosphorus pentachloride. Pentachloride because there's 5 chlorines there. So phosphorus pentachloride. You may have come across that shape in topic 3. It's a trigonal bipyramid shape. So we know that chlorine has got an oxidation state of -1. We have 5 of those. Therefore, the oxidation state of the phosphorus must be +5. Let's have a look at ammonia. Ammonia is NH3. Think back to topic 3 off the top of my head there. That is a trigonal pyramid structure. So we've got there, hydrogen has an oxidation state of +1. There's 3 of them. Therefore, the nitrogen must be -3. Let's look at nitric acid. So we know that hydrogen has a +1 charge, an oxidation state of +1. Let's look at the oxygen first. Each oxygen has an oxidation state of -2. That makes -6 all overall. So we've got a -6 charge here and a plus charge there. If we only had hydrogen and 3 oxygens in this particular case, that would be -6 plus 1. That's -5 overall so far. Remember, this is a compound, so it must be neutral overall. Therefore, the nitrogen there, in this particular case, must be +5. Let's just do a double check first. +1 plus 5, that's +6. -2 minus 2 minus 2, that's -6. So we must have correctly assigned the oxidation states. So if you're asked an exam, what is the oxidation state of hydrogen? You will write down +1. If you're asked what is the oxidation state of nitrogen, you'd write down +5. If you're asked what is the oxidation state of oxygen, you write down -2. You do not write down -6, you write down -2. Let's look at this one. This is hydrogen sulfide. So hydrogen has an oxidation state of +1. There's 2 of them. Therefore, the sulfur has an oxidation state of -2. Let's look at a more complicated one. We're going to look at an ion now. This is the sulfate ion. The sulfate ion has a 2- charge. That 2- there is a charge on all of that. Not just the charge on an oxygen here. It's on the charge of all of that. So overall, the charge must come out at -2. So we need to check that at the end. Each oxygen has a charge of -2. We've got 4 of them. 1, 2, 3, 4. That's -8 overall on the oxygens here. Therefore, the charge on the sulfur must be +6. It's not +8, because if it was +8, that would give no overall charge. We need an imbalance of -2. So it must be +6. Because if we add those together there, we get -8. This is -8. This is +6. 6, take away 8, is -2. So the oxidation state of the sulfur is +6, and the oxidation state of the oxygen is -2. Let's have a look at 2 forms of a compound. So we've got black copper oxide, which is CuO, and we've got red copper oxide, which is Cu2O. Now we know that oxygen has got a charge of -2. Because we've got a different number of coppers in each equation here, then the oxidation state of the copper is going to be different in each one. It must be +2 in this one to balance the charge, but it only must be +1 in this one because we've got 2 of them to balance the charge. Therefore, we'll call this one copper Roman numeral 2 oxide, And this one here is copper Roman numeral 1 oxide. Copper 2 oxide, copper 1 oxide. They have completely different properties. In fact, they're different colours. That's black, and that's an orangey red. Okay, let's look at some more advanced ones then. Now this is an acid that you don't need to know the chemical formula of. It's phosphoric acid. So the most obvious thing to realise straight away is that each hydrogen has a +1 charge. Each oxygen must have a -2 charge. I've got 4 of them. 1, 2, 3, 4. Let's work out the total charge on the hydrogens. So it's +3 on all of those hydrogens there. And it's -8 on all those hydrogens there. There's no overall charge here, unlike this ion here. Therefore, the oxidation state of the sulfur must be +5. We can just check that by going 1, add 1, add 1, add 5. That's +8. -2, -2, -2, -2. That's -8. So a +8 on the H3P, and then a -8 on the O4. So we know we've calculated that correctly. Let's practice some calculating oxidation states of some elements in compounds and in ions as well. So let's start off with iron in iron. So the oxidation state of iron in iron would be 0 because it's an element just by itself. What about iron in FeCl3? Well, each chlorine is -1, so each ion would be +3. What about iron in K2FeO4? Well, each oxygen is -2. Group 1 element is always going to be +1. Therefore, iron here must be +6. So the answer is +6. Sometimes you might see something like this. You come across these more often in year 13. These are called complex ions. What we've got here is a 2+ charge on all of that. Notice the square brackets, because inside those square brackets you've got brackets. So you've got an Fe, 6 water molecules, and all of that has a +2 charge. So let's work out the oxidation state of the ion in this complex ion here. Let's have a go at that one. So each water is a molecule. So the water must have no charge. So 6 times no charge is just going to be 0 again. Therefore that ion there must have the same charge as this one out here. So the ion there is just +2. So we don't really need to work out what the oxidation state of the hydrogen is and the oxygen is there. Let's look at chlorine. Chlorine is an element. All elements by themselves always have an oxidation state of 0. So chlorine here is 0. Let's however look at chlorine here. So it has an overall charge of -1. Each oxygen has a charge of -2. That's -6 overall, because I've got 3 of them. Therefore the chlorine must be +5 to give it an overall charge of -1. Cl2O7. What we've got here is we've got chlorine chemically bonded to oxygen. So each oxygen must be -2. So there's 7 of those there. That's a charge of -14 on all 7 oxygens. Therefore, the charge on this here must be +14. Because I've got 2 of them there, each of them are +7. So chlorine has got an oxidation state of +7. Cl2O3. Oxygen has a -2 oxidation state, therefore each chlorine must have a +3 oxidation state. The answer is +3. SO2. Oxygen is -2, sulfur must be +4. SO3. Oxygen is -2, therefore sulfur must be +6 in this particular case. What about nitrate? NO3-. Each oxygen is -2, therefore the nitrogen here must be +4. +5 rather. Has to be +5 to give an overall charge of -1. Carbonate. So this is the carbonate ion. Carbonate has an oxidation state overall of -2. So each oxygen is -2. There's 3 of them. So carbon here must be +4 to give an overall charge of -2. So Cr2O3. Oxygen is -2. Each chromium must be +3. MnO4 2-. Each oxygen is -2. Therefore the manganese here must be +6 to give an overall charge of -2. Potassium hydride. Remember, everything in group 1 always has a +1 charge. So in this particular case, this isn't a hydrogen ion, this is a hydride ion. Hydride ions have a charge of -1. Okay, we've got 2 metals here and a non-metal. Each chlorine is going to be -1. Everything group 1 is always going to be +1. It's got no charge overall, therefore the copper here must have a charge of +1.